We're live. Doing the chain rule today. So the chain rule. We have a function inside of another function, and we need to take the derivative. Now, fortunately, you do not have to know how to do the first principles derivative for the chain rule. So, but you do have to take it on faith that this actually works. There are a couple of ways of symbolizing this. G at x is the inside function. I take whatever comes out of g for any value of x, and then I put it into the outside function. Okay, this is a second way of symbolizing it. These two functions compose together, and sometimes it gets called fog of x. This means we do perform the function g first on the value of x, and then we do the f. Is there something I need to know? Okay. Oh, it used to be used, now it's g's? Oh, okay, all right. Oh, okay. That's too bad because actually I had G and I replaced it with U just so that it would be consistent. I originally had G here. There we go. Okay. The internet's just being bad. Yeah. And so just so that it was consistent over here, I changed that to U. And I originally had G. Isn't that interesting? And you guys changed it back to G. Okay. Oh, yeah, look at that. It's, oh, I'm not going to say what that is of x. Okay. So here we are. This is the example. I have a function taking the square root of something. This something happens to be a function of x. And in this case, it's x squared plus 2. I can take the derivative of f with respect to x. In other words, how fast is the function f changing as x changes, by taking the derivative of f with respect to u and multiplying it by the derivative of u with respect to x. Okay, in other words, the rate of change of the outside function with respect to the inside function multiplied by the rate of change of the inside function with respect to x. Okay, so if the inside function is changing fast with respect to x, and we put it into the outside function, we're going to be multiplying those two rates of change together. So that's kind of what it means. Okay, so, okay, so taking a look at the ones that we've got there, df du is equal to 1/2 times u to the negative 1/2. So just using my power rule. And du dx is equal to 2x. Okay, so df du is 1/2 times u to the negative 1/2. And this is all multiplied by 2x. But now I actually have to realize that u of x is x squared plus 2. And so I'm going to rewrite this as, I'm going to substitute back for my u like this. So there's kind of an initial answer, and I might want to take that and refine it in form just a little bit. These 2's are actually going to cancel, and so this winds up being x on top, and this is on the bottom because that's a negative exponent, and it's the square root of x squared plus 2. Okay, so that is the derivative of f with respect to x when x was inside of that function. Okay, let's move on. Oh, are we good? Press pause now. So let's find an appropriately ugly function. And we are going to figure out what the outside function and the inside function are. So we're just going to use y instead of f this time. 3x squared minus 7x to the 5th. Okay, so I want to know what is my outside function and what is my inside function. Okay, So I'm going to figure out what my inside function is. Internet, anybody? What's my 3x squared minus 7x? That is my inside function. It's a function of x. And this is u. And what is my outside function? U to the exponent 5, yeah. Okay. And if I want to know the rate of change of y with respect to x, I'm going to take the rate of change of y with respect to u, and I'm going to multiply it by the rate of change of u with respect to x. Okay. So I'm going to move this down. It does not hurt to have a nice little stable where you do this off to the side. Okay. dy du is 5u to the fourth. Du dx is 6x minus 7. I'm going to go over here and I'm just going to put in dy du, 5 to u to the fourth, and then du dx is 6x minus 7. But I'm going to remember that u is a function of x, and I'm going to substitute that back in, and this becomes 3x squared minus 7x to the fourth. Okay.
Where it says dy, do we straight up put in u to the fifth, or do we take the derivative so it would be 5u to the fourth?
So this is saying take the derivative.
Oh, that whole like dy over du.
dy over du is the derivative, so that's the Leibniz notation for the derivative of y with respect to u. Okay, there we go. Hardest part, identifying what the outside function and what the inside function is. Otherwise, this stable of stuff over here stays perfectly in place. Okay. Now we're going to have a function of x rather than like a y equals thing. And this is going to be 4 times 3x minus 2 to the exponent 5 minus 9. Now I have to figure out what my outside function is, what the derivative of that is, and I have to figure out what the inside function is and what the derivative of that is with respect to x. Okay, here we go. What's my outside function? 4u to the power of 5 minus 9. So I guess I could have identified my inside function first. So u is 3x minus 2. I'm going to take this derivative of f with respect to the inside function, or with respect to u. So this becomes 20u to the fourth. And the derivative of a constant is 0. So that's easy. And now I'm going to take the derivative of du dx. And it's just 3. The derivative of negative 9 is 0 because it's a constant. All right, just change this notation around a little bit. df dx is going to be df du times du dx. And now that I've put my little stable of stuff over here, df du is 20 times u to the fourth. And I'm going to multiply that by du dx, which is just 3. Now I'm going to do my substitution back for u, because I know that u is 3x minus 2, so this becomes 20 times 3x minus 2 to the fourth, and then that is multiplied by 3, so it simplifies down to 63x minus 2 to the exponent 4. Okay? You will eventually get to the point where you don't even do this, break it up into the two functions. You're just going to actually look at it. And you can probably do it without doing this, but for now, I think it's a good idea to break it up into those two functions. Okay. Last example. It's going to be the luxury case. So we're going to make this one into y instead of f. Okay, so y is equal to square root of, once again, the radical notation, 3x cubed. Oh, that's a cube, not like a horribly disfigured 8. 3x cubed plus 6. And then I'm going to figure out what my inside function is, and internet, what should I choose for my inside function here? 3x cubed plus 6. Okay, so that means if u is 3x cubed plus 6, then I'm just taking the square root of u, which we all know is equal to u to the exponent 1/2. Because that radical notation, it's just dumb. All right, I'm going to use my power rule when I take the derivative of y with respect to u. Simple enough. And here we've got du dx. So this is going to be 9x squared, and the derivative of a constant is 0. Dress this up a little bit, and we're ready to roll. Okay, the derivative of y with respect to x is equal to dy du, which is just 1/2 square root of u. See what I did there? And then I've got du dx, which is just 9x squared. Oh, but this u, I can rewrite that in terms of x. And so u is just 3x cubed plus 6. I have to extend that a little bit. And this is over 9x squared. Okay, so this becomes 9x squared over 2 times the square root of 3x cubed. Oh, yeah, 3x cubed plus 6. All right, so there's the derivative of that. So we can turn this into a luxury program by saying, what is the slope when x is equal to 1? To that function right there. Okay. So we can extend it a bit. What is the slope of the tangent? To y equals the square root of 3x cubed plus 6 when x equals 1, question mark. That's easy. Of course, I chose x to be 1. Okay, so dy dx is equal to 9 times 1 squared. That's 2, right? No, it's not 2. It's only 1. Somebody, oh, there we go. 3 times 1 cubed plus 6. Okay, so this is 9 over 2 times the square root of 9, which is 3/2. So that's the slope of the tangent when x is equal to 1.
So all you're doing is inserting whatever value for x.
Whatever, yeah, that's all you have to do.
See, this is like a good lesson. Yesterday when we did that was a terrible lesson. Just numbers come out of everywhere.